So let us move on to the next plenary lecture. That will be given by our own Professor Bikramjit Basu, Director CGCRI. And this lecture is dedicated to Dr. S. Kumar, Sachidananda Kumar, the former Director of CGCRI. Just let me add just 2-3 words, that is 2-3 lines. That I joined CGCRI in 1984, then he was the Director, Dr. S. Kumar. He was a great visionary. And he initiated this fiber optics lab in the institute, and I, Dr. Ranjan Sen is here, so we joined there, and slowly we built up that laboratory, what you see today. Perhaps some of you have seen that. And Dr. Kumar did a great work in compiling the handbook of ceramics, the volume, I think it's 4 volumes. It's a great one, and for students, it's a very good book. And another thing is, around 1960s and before that, so Sheffield Group, already we discussed yesterday, Dr. Kumar was in Sheffield, and they worked under Professor Douglas, a great professor and glass scientist. And Dr. Kumar, he published a lot of papers when Journal of Non-Crystalline Solids, if you look at during the early 60s papers, the metal doped glasses. It's a tremendous work he did at that time. Then he came to CGCRI and joined, and he built his career. So with these brief words, now I request Professor Basu to, and Professor Basu already, already we know, and we have a lot of hope and dream. Since he joined CGCRI, he got a lot of awards, including Bhatnagar Award, the prestigious top awards from this country. And he's a member of all the national academies and abroad also some of the academies. So with these brief words, I request Professor Basu to deliver his lecture. Professor Basu, please.
So, good morning, everybody. At the outset, I wish to express sincere gratitude to Professor Dr. Bhadro to introduce me. So, today what I'm going to do, first of all, I would like to mention a few more things about Dr. Kumar. So, he is a PhD and DSc from Sheffield University, UK, and in that period of time, Sheffield University was really very strong in the ceramics and glass, and then he was also one of the directors of CSIR-CGCRI, and he played a crucial role as the president of the 14th International Congress of Glass in 1986, as mentioned by Professor Arun Bhasne. Secondly, it is very difficult to follow up Professor Arun Bhasne, who is globally known as a glass guru. And I would like to mention 1 or 2 of my things from my personal perspective. For last 16 to 17 years, I have been regularly traveling to American Ceramic Society conferences. I have been also serving in several committees of American Ceramic Society, including the International Strategic Committee and so on. I know many Indian origin ceramic and glass scientists from US and elsewhere in the world, but I regard Professor Arun Bhasne as one of the finest human beings. He is extremely humble, polite, despite of his stature. I'm not trying to tell all these things to please him. Please take my words. So he never ever tells about his, whatever awards he got and all those things, but he's extremely fine gentleman. And often I give a lot more importance to a researcher that how nice and how good as human being, because that is our whole soul of purpose. Second thing about Professor Arun Bhasne is that, again, in all my interactions I have seen that he has a keen interest to help Indian scientific community to grow, particularly in the field of ceramics and glass. And he has been consistently doing it whenever such situation comes. and he has been very generous in his supporting the Indian scientific community as well. Thank you very much, Professor Arun Bhasne. So, having said that, this is the plan of my presentation. So first I'll present before you some of my early work on the multi-component glass ceramics for dental restorations, followed by some of the biocompatibility studies on glass ionomers. Third one, recently we have developed some quantitative models for bone formation. In my current role, I must tell some more things about the science, technology, and innovation activities on glasses and fiber optics. And following that, I would like to emphasize that why we need to develop a vibrant ecosystem in these particular areas. Now, clinical perspective, glass ceramic materials are used as crowns in the dental restorations. In my own research group at ISC Bangalore, we have developed dental implants. We have developed titanium implants, which have been already clinically tested on 48 human patients in 3 different states, Karnataka, Maharashtra, as well as Uttar Pradesh. And we are currently developing zirconia-based dental glass ceramics, zirconia-based ceramic implants as well. So biocompatibility is the primary properties of relevance, followed by mechanical, chemical, solubility, and wear resistance. So this is the work that we have started in IIT Kanpur many years ago. So when Shiba and Atiyar, they are like MTech students in this particular, and who have contributed to this particular research area. So these are the glass ceramics which is used as dental crowns, like alumina reinforced porcelain, lucite glass ceramics, and so on. So one of the materials that we have investigated quite a bit is the macro glass ceramics. So it's a multi-component silicon oxide, silica, alumina, magnesium oxide, K2O, B2O3, and fluorine. Now, fluorine is one of the major things that we try to tune and try to find out that how fluorine content influences both microstructure development as well as the properties. Now, after Siban's work, when Atiyar started working in my group, and then we developed some fascinating microstructure, which we called envelope-like crystals, envelope-like microstructure, where the crystals are growing from all different directions, and they suddenly they stop. It is like exactly like envelope, like when we used to write letters more than 20 years ago, and we used to put it in an envelope and send it to the sender. So that kind of microstructure we developed. It's still intriguing to me that how to simulate this kind of microstructure, both from modeling aspects. And that is some of the things we would like to also pursue in near future. Now, around 7 or 8 years back, one clinician scientist in Bangalore from Ramaya University of Applied Sciences approached me, and she has very keen interest to work in the biomaterials and implants. So we started developing 2 different types of glass materials. Again, by varying the fluorine content, in one case, which we call 1% fluorine content, and one case it is 6% fluorine. So we call it is a G1 and G2 glass ceramics. So essentially, we're trying to understand that what is the critical effect of fluorine on the crystallization of this fluorosilicate glass ceramic system. And being a metallurgist by training, we know that what is the process of nucleation and growth. And here, this nucleation is more like a droplet kind of things, and then as they grow, they take a specific shape. And this particular specific shape that grows, but it cannot grow infinitely, as I mentioned to you, there are 2 slides back, that it leads to this particular different kind of microstructure. So this is Dr. Gali, who is a Wellcome Trust DBT India Alliance clinician scientist in my group. So she has developed this kind of glass ceramic materials, but again, we have reinforced with zirconia with the hope that particularly if we stabilize tetragonal zirconia, there is a clear chance of having little higher fracture toughness in these materials. Hardness-wise, if you see, it has reached the hardness of around close to 9 to 10 gigapascal. And if you know that some of the commercial dental crowns, they have like around 9 to 9.5 gigapascal. Here again, we have particularly investigated the influence of aspect ratio and also crystal content, and how they are correlated with this material, how they are correlated with the hardness properties of this material. Now, if you look at this natural material, like enamel, it has a hardness of 2 to 3 gigapascal, and then we need to develop a material where it's veneer ceramic, as a coarse ceramic has very different kind of hardness values. Now, if you look at this further other properties of relevance like elastic modulus as well as the fracture toughness, now elastic modulus wise that, there is not much difference, but, fracture toughness, we have used indentation fracture method as well as single edge V-notch beam technique, and which is already reported in some literature. And in indentation fracture, we are able to measure somewhere around 3 to 4 MPa square root meter. But when we did this further ACV and B, we got almost like 1.8 to 2 MPa squared, which is marginally higher than some of the materials that was already reported in the literature and so on. So as Arun has also mentioned about the brittleness index, so we are trying to understand that whether this material is machinable, and to be machinable, brittleness index must be less than 4.3, and most of our materials, they had in that safe window is around somewhere around 3 to 3.3 micrometer inverse, or by square root of the micrometer. Now let us move on to the next one, this glass ionomers for bone regeneration. As part of the UKRI, that UK India Education Research Initiative with University of Birmingham, we have developed these glass ceramic materials, and with particular composition is more on the clinically relevant composition, that 4.5 silica, alumina, phosphate, calcium oxide, and calcium fluoride. So the major task here to understand and also to understand the bone regeneration capability of these glass ionomer materials, and whether if we substitute or if we substitute by calcium with strontium, how it will help in bone regeneration, and therefore we have developed also 100% strontium substituted glass ionomer cement. So when I put it in the rabbit model at different implantation time, 4 weeks, 12 weeks, and 26 weeks, and we are particularly interested to see that how this host bone, so this is the host bone, like this is the rabbit's natural bone, and when this material is implanted, this is our essentially the artificial or glass ceramic materials, how this bone grows at different time points starting from 4 weeks to 12 weeks to 26 weeks. This we have investigated further using microcomputer tomography analysis, which can allow you to quantitatively understand bone volume by total volume. So bone volume by total volume is 0.62 at 4 weeks, then it goes to 12 weeks, then it goes to 26 weeks. You can see bone volume to total volume increases up to 0.93. So more importantly, we are also scaling these micro-CT images with different color contrast to see how bone tissue in different thickness, they grow at different time point. So this color scheme essentially tells you that 1.7 mm is the maximum bone tissue that grows into around the scaffold or around the implants after 4 weeks of implantation. It is roughly same, and 26 weeks also it has grown further. So based on all our work, what we try to understand that how to quantitatively analyze this bone growth. And before I go to this bone growth model, there's a lot of mathematics in it, so I'll go a little slow here. But we need to understand that when bone forms in the materials, there are two types of cells. One is osteoblast cells. Osteo means bone. Osteoblast means bone-forming cells. And there is another cell type is called osteoclast cells. Again, osteo means bone, and clast means bone resorption cells. So it's a competition between these two types of cells. One cells will essentially enhance the bone formation. Another cells will essentially degrade the bone. So if there is osteoblast cells are more active, then bone formation will be much more facilitated. Having said that, there is also two types of things that one needs to, from cell biology perspective. One is autocrine signaling, like same type of cells will give signaling molecules to same type of cells, so it's auto means same. And it's another type of signaling called paracrine signaling. So there is a signaling cell and there is a target cell. Signal molecules by Fickian diffusion process is being transported to the target cell. So this is called paracrine signaling, that both the source cell and target cells are different. So here, osteoblast cells can give signaling to another osteoblast cells. It is called autocrine, and in osteoblast cells give signaling molecules to osteoclasts. That is called paracrine cells, paracrine signaling. So both these kind of signaling mechanisms are equally active. Now let's go to this mathematics very slowly. So this is the y as a function of t, while y is a bone volume that is formed as a function of t. So first differentiation, dy by dt is equal to k2 x2a minus k1 x2a. So k1 and k2 are essentially normalized activity of bone resorption, which is mediated by osteoclast cells, and k2 is the normalized activity of bone formation, which is mediated by osteoblast cells. And therefore, we can also consider this first, this x1a, which is again a function of time, which is x1t minus x1 bar, and x1 bar is essentially steady state value of osteoclast. Similarly, one can also follow this particular equation, which is nothing but temporally varying osteoblast minus the steady state values of osteoblast. And if you put this, if you do simple mathematics, if you plug in this one here, then you get this particular equation. And this particular equation, certainly we can write it in the form of autocrine and paracrine signaling, and we get these different constants like G11, G21, and that we have followed this particular paper which was published in 2003 in one of the flagship journal called Bone. Now we did all this mathematics and we found out that given these particular parameters in this table, we found out that y as a function of t is not a linear equation, but it is more like a parabolic type of equations where first x1, so c1t minus c2t square, where c1 is 6.598 and c2 is 0.2338. Now when you have plotted particularly Mark Bonar's group from RMS Foundation Switzerland in our collaboration. So this beta TCP bone substitute, which is implanted in the SIP model, and they have published several papers in Biometrics and Acta Biometrialia. So when I was having a dinner in one of the conferences in Belgium, so he suggested that, why don't you start developing quantitative understanding of the bone formation models? Then we exchanged a lot of data. We developed all these theoretical models in my group, and then we started fitting this data. And it fits relatively well with this quadratic fit of 0.989, and you can see these particular things, it goes down. So it goes up because there must be, whenever any curve goes up and then further goes down, there must be a transition in the mechanism. And here, this transition mechanism is the way this bone forms. So this bone formation essentially first is more trabecule-like woven bone formation. It is like a very spongy coat type of mechanism. Then it goes to lamellar bone growth mechanism, and this transition essentially shows that bone formation goes through this kind of lamellar growth mechanism. If you see that particular materials that I have shown in last 4 or 5 slides, 4 weeks, 12 weeks, and 26 weeks, it goes essentially linearly in the same, almost linear in the same manner, and it is essentially in this week. But we still do not understand why 26 weeks does not fall the way it has fallen it here. Because it is a different type of material. One is a beta TCP, which is a bioresorbable ceramic material, and this is a glass ceramic material which is not as bioresorbable as the beta TCP material itself. Now, from mathematical point of view, as I go back to remind you of these equations, now if you see here, there is a multiple terms are involved, like yt is equal to c1, c2, k2, k1, and so on. And many of these terms are related to this kind of autocrine signaling coefficient, paracrine signaling coefficient, and all. When multiple parameters influence the value of the parameter which is at the left-hand side, then we have to understand what is the sensitivity or parametric sensitivity of each of these parameters. So first of all, we have investigated that what is the parametric sensitivity of the osteoclast growth rate, that is alpha 1, and osteoblast growth rate. And if you look at the scale is same, and you can see there is not much significant increase if we change these alpha 2 values or alpha 1 values within a reasonable level like 0 to 6. Now, if you look at the other one, that how this osteoclast is removed during the bone formation and how this osteoblast is removed during the bone formation, we do see there is a reasonable sensitivity of bone formation towards changes in beta 1. Particularly beta 1 is equal to 0. It was very sharp and steep, but when then it falls when beta 1 essentially goes from 0 to 0.6. Same is true for beta 2 as well. In the beta 2, you can see it's much more linear, then it suddenly slope drops down when it goes increasing from 0 to 0.6. So essentially the conclusion or major message is that it is sensitive, bone formation is sensitive to both beta 1 and beta 2 as well. Now, as I mentioned to you before, that there is a kind of autocrine signaling mechanism, and autocrine signaling mechanism of osteoclast means osteoclast giving signals to osteoclast, osteoblast giving signals to osteoblast. In both these cases, G11 and GT2, you can see there is hardly any sensitivity in case of G11. However, in case of G22, you can see this is minus 1.0, this is the minus 1.0, and then when it goes to positive, like G2 is equal to 0.25, it drops off. So therefore, this bone formation is more sensitive to the osteoblast autocrine signaling, and that is very much commensurate with our fundamental understanding of the bone biology. Now, if you move to so essentially what we have learned, that for the paracrine signaling, so I have just shown you for the autocrine signaling. For the paracrine signaling, so for the paracrine signaling, I would like to remind you that osteoclast is giving signals to osteoblast, that is G122, and osteoblast giving signals to osteoclast, that is G21. So G12, there is not much sensitivity. However, when osteoblast gives signals to osteoclast, you can see there is a very clear sharp increase and very different trend when G21 is 0. However, when G21 is more negative, then it drops off. So therefore, sensitivity of the bone formation towards osteoblast is very clear. Now let's move on to some of the science technology innovation initiatives of CSIR-CGCRI on glasses and fiber optics. So one of the things that I have mentioned yesterday as well, and today I would like to also mention that this is the specialty glass division which has started its particular work in radiation shielding window glasses when Dr. H.S. Maiti was our director, and then it has been transferred to BARC, Bhabha Atomic Research Center, NIDM laser glass for high energy, high power applications. RRCAT DAE is one of our national lab collaborator. Dr. Chandrachud is here. Then 2023, chalcogenide glass for thermal imaging, Dr. Annapurna and Dr. Kaushik was started, and this has been going on. More recently, it is the space-grade optical glasses. Two things I would like to mention here. One is that homogeneity in the space-grade optical glasses should be of the order of 10 to the power minus 6. 10 to the power minus 5 homogeneity is even not accepted by ISRO, but we are trying to go slowly towards that 10 to the minus 5 to 10 to the power minus 6. Second one is that their optical properties needs to be matched up to 3 to 4 decimal places, particularly the RI values, and that is even more challenging of these particular classes. So these Dr. Annapurna and Kaushik, they are essentially trying their way out to match both these requirements for ISRO, Indian Space Research Organization. And their properties are being also validated at ISRO as well. The second one, that we need to essentially align that glass technologies to more to the pressing national needs. Like many Indian industries currently venture into solar glass, glasses for automobiles and armor glasses. And more importantly, bioactive glasses and glass ceramics for healthcare application. This is something I wish scientists at Specialty Glass Division should start as long as I am there at CGCRI, so that I can essentially mentor this particular area of development. There is also some activity from Nilay Lakhar's group at Synthera Biomedical Private Limited that is based in Maharashtra. So they are into the also glass ceramic materials, particularly bioactive glass ceramics for healthcare applications. The other thing, it is also equally exciting for me if CGCRI scientists would develop more understanding and more work on the modeling and machine learning approaches for the structure property, process property correlation prediction, as well as structure prediction of multi-component classes. And many of these things are essentially aligned with the Make in India initiative. This movie does not work, I don't know. Okay. So this is another work that our glass division scientists have also aligned their activities, that is the energy research. So hydrogen technology or green hydrogen technology, which I have particularly mentioned in yesterday's inauguration lecture, that is one of the major things, and there are two areas there, solid oxide fuel cells and solid oxide electrolyzer cells. Both these particular technologies are being developed, and we have also transferred one such technology to QMI, Carborundum Universal, and their division head is Dr. Jayanta Mukhopadhyay. So if you look at their journey from 2016, we are currently at 2025. They have already close to develop the 2 kilowatt class stack, and in 2020, in the 2026-27, they would like to go further for the 10 kilowatt prototype. That is as far as the solid oxide fuel cell technology is concerned. Now, in the solid oxide electrolyzer cell technology, it started quite late, but they are doing pretty well, and I'm very happy to tell you that at least 2 kilowatt solid oxide stack with external and internal manifolding is completed. Here again, they are working with industries like HPCL and so on. And this particular work is being closely mentored by Dr. Shivram as part of the CSIR hydrogen technology mission. But why I'm mentioning about the energy in between, because the glass sealant materials which CGCR has developed, that is barium-free glass ceramic sealant, the challenge is that coefficient of thermal expansion values of the sealant should be intermediate between 8 mole per nitrous stabilized zirconia and copper 22 APU. So it has to be tuned between 10.6 and 11.9 into 10 to the minus 6 per Kelvin. And they have developed these particular sealant materials, and they have also tested number of thermal cycles here, at least up to 15 number of cycles, to see that how this voltage output is being monitored within a very close window. Now, fiber optics and photonics division at CSIR-CGCRI, Dr. Bhadro has really given pioneering leadership during his tenure at CGCRI, and currently Dr. Somnath Bandyopadhyay is the division chair. I must mention to you, many of you are already aware, but those who are not aware, this is the only research division in a national lab in India with decades of core competency on optical fibers for lasers and sensors. And this has many decades of significant contributions to strategic and private stakeholders. And Indian industries currently seek new optical fiber-based lasers. As I'm speaking to you today, DRDO is planning to develop a large center of excellence on these fiber optic lasers, and it will be several crores because many DRDO labs are currently seeking this kind of fiber optic lasers. And it is one of the most performing divisions at CSIR-CGCRI, and you can see in terms of numbers 21 to 24, it has 89% of the total funding comes from industrial and government-funded projects. In CSI language, it is known as external cash flow. Now, again, this I think video will not work. ওটা দেখো তো চালাতে পারো কিনা ভিডিও চলছে না Okay, just to give a glimpse of these fiber lasers for healthcare and strategic sector applications, they have one of the industry partner called Allengers that is based in Chandigarh. They have taken their technology, and this is essentially based on thulium fiber laser for healthcare-related applications. And this thulium fiber laser has been very useful clinically, and they have clinically tested for fragmentation of the urinary stone or prostate tissue. You can see the prostate tissue after the laser surgery. Then there is a continuous ytterbium fiber laser. Again, their industrial partner is Omega Innovation. And currently, the power is 1 kilowatt. And recently, they have got around 15 crore project from the DRDO on this particular fiber to essentially scale up that total power. They want at least 2.5 to 3 kilowatt. There are other type of lasers that they have developed, and also most importantly, they are also interested to apply that artificial machine learning in this particular area of research. So what is the challenge? Whenever any government organization like MeitY, that's Ministry of Electronics and Telecommunications, they have funded a center for innovation in this particular area, and that will be essentially established as CGCRI. They are interested that how many companies will come forward and take their technologies, and then we see number of companies in India who would be very interested to take, and who has also required expertise to take it forward from TRL 4 or 5 to TRL 8 or 9, those kind of companies are less than 10 even. So we need to see that how different companies and startups will absorb these technologies. Absorb is a better word here, because it is not only the companies may have certain manufacturing facilities, but they should have the expertise to absorb these technologies, and they should be able to interact with the CGCRI scientists. That is more important. Now, in terms of ecosystem development, I would like to conclude by essentially showing you that how CSIR-CGCRI in next few years would turn into a national hub of glass at CSIR in India. And here we have been collaborating with several CSIR sister labs like NCL Pune, particularly in the energy sector, NML, ICB, CMR, and so on, in different companies like Prism Johnson, Saint Corbin, Borosil, and also the different strategic sectors like Department of Atomic Energy, DRDO, ISRO, and so on. But we need to grow these kind of sectors much more, and more interactions need to take place in the years to come. Because two things I want to mention: there should be more interactions with academia for innovation-driven technologies, and also CSIR wants us to generate more external cash flow. That is also one of the challenges that our researchers have taken. Now, more importantly, these ICG-like platforms or American Ceramic Society-like platforms are unique platforms which can project CGCRI activities to the globe and to the world, rest of the world. Many times when I go to American Ceramic Society conferences, I find that quantum and quality of research that we are doing in India is still unknown to the global community to the extent that they should know and appreciate the work being carried out in India. So there is certain gap, and that gap must be filled by with conscious efforts from researchers from India in next few years or so. So another thing is that engaging with the key stakeholders. So we are constantly working with several companies. India is a large country, so north, east, west, south, in different areas, different companies are working very closely with many industries here. Now, how this ecosystem will grow? One of the major things for this ecosystem to grow is to do very high-quality scientific research in tandem with indigenous technology development. And what I mean by high-quality scientific research, we need to also develop more expertise in the computational modeling aspect. So it is a molecular dynamics simulation. That is one of the things that glass scientists have started doing and exploring more and more. So molecular dynamics simulation is essentially interatomic potential. You need to optimize the interatomic potential. There is different components of the interatomic potential, like bond vibration, bond bending. There is a torsional term, and this one is a very popular term. That's Leonard-Jones potential term, and also there is the electrostatic interaction term. There is one student at IISc Bangalore in my group who started this work few years ago, more than 6 to 7 years ago, and we have published a series of papers using molecular dynamics simulation. So I was very interested to see that how molecular dynamics simulation work can be extended to ceramics and glass community at CGCRI. So Indrajit is currently doing a lot more work at CGCRI on the MD simulation, and our idea is that how MD simulation results will produce large quantum of data which can be essentially fed into machine learning algorithms, and how machine learning algorithms can allow us to predict the structure in a much more accelerated manner. Once we understand the structure, then we would like to know that how structure property correlation can be established using the machine learning algorithm. So here in particular, this Indrajit's case, this is the Indrajit's work, mean square displacement, diffusion, and structural conformation. These are the three major parameters which are investigated. Just to give you one such result, they have essentially used 3 different glass composition, BG42, C50, and C100. So they are trying to understand that when these glasses are kept at this particular temperature, very high temperature, what is the mean square distance, as well as the diffusivity that evolves. And from the slope of this diffusivity with respect to 1 by t, you can get essentially activation energy. And you can see in one particular case, because of the composition, it has a low barrier for activation. And this one particular case for C100 is a high barrier because activation energy is almost double in 123 kilojoule per mole. Right. So as I said, that artificial intelligence machine learning is something very new to this material science community, at least in India. And this is one of the places that where we can make a large dent, particularly additive manufacturing. This is the example from the 3D printing, where people have used the laser-based 3D printing method by optimizing different parameters by single track and multi-track pool. They can do two types of things. One is a regression model for more like a regression model essentially for the properties, and then classification model that what is the quality of the component, whether there is a crack in the 3D printed components or the, this particular component is the defect-free. So both these regression and classification model is something that one can also use, provided that we have sufficient amount of data. With this, I conclude my talk, and thank you for your kind patience. Thank you very much.
Yeah. Thank you, Professor Basu. It's very interesting work, and you have detailed the activities at CGCRI. So I think time is up, so very difficult to go for questions. So please discuss in the tea time, whatever you want to discuss. So he'll be available. So with this, I think we'll conclude this session. Before that, I want to just one issue. Today, you heard two lectures from Professor Varshney and Professor Basu. In optical fiber, yesterday also I asked these questions, that strength of optical fibers is a very interesting story. When optical fibers were being installed across the Atlantic, from USA east coast to England, it's a 6,500 kilometers length. There, initially they found that shark used to cut the fiber. That is one issue. Another is the strength of the fiber. Now, what I heard, to reduce the strength, increase the strength, now the metal-coated fiber, instead of polymer-coated fiber, they're using the crack growth and all. With respect to time, it grows, so it can be prevented with metal coating. Another thing is to avoid shark bite. They use the armoring and all. So the strength of the glass and the study is really important. Already they have described, and it is very important in optical fiber, what you have seen today installed across the surface and across the globe. So with these few words, once again, I thank both the speakers, keeping the time, and really it is a great pleasure for me to chair this session. With this, I think it's my pleasure to hand over.